All right, buckle up, everybody, because today we're diving headfirst into a question that's plagued philosophers and scientists for, well, probably as long as humans have been looking up at the night sky. What was there before the Big Bang? We've got a pretty cool YouTube video to unpack, one from the channel History of the Universe, titled, What Was There Before the Universe? And yeah, just from the title alone, I'm already getting those existential goosebumps,
Oh, totally. And you know what? Right off the bat, the video does a really smart thing. It spends a good chunk of time just busting some of those common misconceptions about the Big Bang itself, which I think is a really great way to set the stage, before we even try to wrap our heads around what might have come before it.
Right. Like, for starters, it wasn't an explosion in space, was it? I remember the video made this comparison to, like, the universe being smaller in the past, and it's just been expanding ever since. Kind of like, blowing up a balloon. It just keeps getting bigger and bigger from that initial inflation.
Exactly. The point is, there wasn't something exploding into space. Space itself was just incredibly dense, and it's been expanding ever since. And there wasn't any central point for this explosion, right? It happened everywhere, all at once. Think about, like, the surface of a balloon. As you blow it up, there's no one spot on the surface that's the center. It's expanding everywhere simultaneously.
Oh, okay. I see what you're saying. But then there's this whole thing about the Big Bang singularity that kept popping up in the video. So what is that exactly? I mean, in plain English.
Well, imagine trying to use our current understanding of physics. All those equations and laws we've come up with to describe the universe at the very, very beginning, like that incredibly tiny, incredibly dense starting. Yeah. What happens is our equations just sort of break down. It's kind of like trying to divide by zero on a calculator. You just get an error message. And that error message in physics, that's what we call the singularity.
So it's basically like a point where everything we know just stops working.
Precisely. And honestly, that's actually pretty exciting because it means we need new theories, new ways of understanding the universe to truly grasp those earliest moments.
That actually reminds me of something else the video brought up. All that buzz about the James Webb Space Telescope and how some people were claiming it disproved the Big Bang, which we know isn't true at all. It's like playing telephone. By the time the information gets passed around, it's completely distorted.
Oh, for sure. I mean, it's a good reminder to be critical of what we read, especially when it comes to these complex scientific topics, right? Like new discoveries are constantly.
All right, so we've debunked a few Big Bang myths. That's a good start, but we still haven't even touched on what might have existed before it. Now, the video brings up this concept of inflation, which the word itself sounds simple enough, but it gets pretty complicated quickly.
Oh, yeah. Basically, the idea is that in the tiniest fraction of a second after the Big Bang, the universe expanded at an unimaginable speed. We're talking faster than the speed of light, like exponentially fast.
Wait, hold on. Faster than the speed of light? How is that even possible? I thought nothing could travel faster than light.
Well, that's the thing. It's not about things moving through space faster than light. It's about space itself expanding. It's a tough concept, I know.
All right. So the universe went through this massive growth spurt right after the Big Bang. Got it. But the big question is why? What caused this insane expansion?
That's where this physicist, Alan Guth, comes in. Back in 1979, he proposed this idea of inflation as a way to explain some big puzzles that the classic Big Bang model just couldn't account for.
Oh yeah, I remember this part. It was things like, the universe looks pretty much the same in every direction, which is weird because those distant regions, they shouldn't have had time to talk to each other to even out their temperatures.
Exactly. That's one of the big mysteries.
Yeah.
Like, how did the universe get so uniform in temperature and structure?
Right.
And it's incredibly flat, too, on a large scale. Those were huge questions. But inflation offers a potential solution. The idea is that if the universe expanded super fast, early on, it would smooth out all those initial irregularities. Kind of like when you blow up a wrinkled balloon, those wrinkles disappear once it's big enough.
Okay, that makes sense. So how does inflation actually work? What's driving this rapid expansion? The video mentioned something about scalar fields, but honestly, that part went a little over my head.
Right, scalar field. Think about like a weather map. You know how it shows the temperature across a country?
Yeah.
So each point on the map has a specific temperature value. That's basically what a scalar field is. It's a way of assigning a value to every single point in space.
So it's like a map, but instead of showing elevation or rainfall, it's showing something else. And that something is what's causing it.
You got it. Guth proposed that there was this special scalar field, sometimes called the inflaton field, which was responsible for this expansion. So just like the Higgs field gives particles mass, this inflaton field had a very high energy state, which made the universe inflate like crazy.
Okay, I think I'm starting to wrap my head around this, but is this inflation idea just a cool theory? Or is there actual evidence for it?
Well, that's where things get even more interesting. Remember how we talked about the cosmic microwave background? That faint afterglow of the Big Bang?
Yeah, like a baby picture of the universe.
Exactly.
Oh.
In 2013, the Planck satellite made some incredibly precise measurements of tiny temperature fluctuations in this background radiation. And guess what? Those measurements match the predictions of inflation perfectly, like with incredible accuracy.
So they had a theory about how the universe behaved in like the first sliver of a second after the Big Bang, and then they actually found evidence for it billions of years later.
Oh.
That's mind-blowing.
Oh, it is. Those Planck results were a huge deal for inflation. There are even pictures of physicists celebrating with champagne bottles with the cosmic microwave background printed on the label. I mean, that's how big a deal it was.
Wow, that's awesome. So I guess inflation's a pretty solid theory then, right? Case closed. Mystery solved.
Well, not quite. Remember, we're trying to understand what happened in the first tiny fraction of a second after the Big Bang. It's incredibly difficult.
Yeah.
And in a way, that confirmation of inflation actually opened up a whole new can of cosmic worms. It led physicists to explore some even crazier ideas, like the possibility of a multiverse.
A multiverse. Now we're talking serious science fiction, right?
It might sound that way, but it's actually a consequence of some of our most cutting-edge physics theory. And that, my friend, is where we'll pick up next time.
Okay, multiverse.
Well,
that's a big one. So you're saying that our universe, this whole massive thing with all the stars and galaxies we can see, it might just be one of many, like just one bubble in a whole sea of universe.
It sounds crazy, right? But yeah, that's what some physicists are actually suggesting. And it all kind of stems from this idea of eternal inflation. The video explains it really well, but remember how we talked about inflation happening right after the Big Bang? That super fast expansion?
Yeah, that crazy growth spurt driven by that, what was it called? The inflaton field.
Right, exactly.
Yeah.
So eternal inflation basically says that this process of inflation, it never actually fully stopped. Like it keeps going in some parts of space, creating this kind of like background of inflating space-time that's always expanding. And within that, new universes are popping up all the time, each with its own Big Bang, and get this, potentially its own set of physics.
Whoa. So it's like a never-ending chain reaction of Big Bangs creating this like sea of bubble universes. And we're just stuck in one of them.
That's the basic idea. And to illustrate this, the video uses this really interesting literary reference, Dostoevsky's The Double. Imagine there are all these copies of you out there in these other bubble universes living out all these different versions of your life.
Wow, that's a lot to process. It's kind of freaky, honestly. But okay, hold on a second. How can we even talk about other universes if we can't even see them? Isn't this just like pure speculation?
Well, it's true that directly observing other universes is a huge challenge. I mean, maybe it's impossible, who knows? But the idea of a multiverse, it actually comes up pretty naturally from some of our best physics, like inflation and also string theory, which we'll get to in a bit. And, even if we can't see them directly, there might be some indirect ways to detect them. Like by looking for subtle patterns in the cosmic microwave background, that afterglow of the Big Bang, there might be signs there of like collisions between bubble universes.
Oh, interesting. So we're looking for kind of like ripples in the fabric of space-time to see if maybe another universe bumped into ours?
Yeah, kind of like that. It's still just a hypothesis for sure, but there are scientists actively looking for evidence.
I can dig it. Okay, so if there are all these other universes out there, potentially with different laws of physics and everything, why does our universe seem so perfectly tuned for life? I mean, it seems like the odds of that happening are pretty slim.
That's the million-dollar question, right? Is what physicists and philosophers have been debating for a long time. The fine-tuning problem, they call it. And, one possible answer, as crazy as it sounds, is that the multiverse itself is the explanation. If there are tons and tons of universes out there with all these different laws of physics, well, then it stands to reason that at least one of them would have the right conditions for life. Right? And guess what? We just happen to be in that one.
So we won the cosmic lottery.
Kind of. It's a mind-boggling concept, I know.
Yeah.
And yeah, some physicists aren't totally satisfied with that explanation, understandably. It feels like a bit of a cop-out to them, like we're just saying, oh, well, there must be a multiverse, so problem solved. And they're looking for other explanations that don't require a whole bunch of other universes. But for now, the multiverse, it's still a pretty intriguing possibility.
I'm with you on that. It definitely makes you think. But okay, before we get too lost in the multiverse, the video also mentions this other crazy theory, right? String theory. The one about like tiny vibrating strings making up everything in the universe.
String theory, yes.
Yeah.
It's one of those theories that's so elegant, so potentially groundbreaking, that it just grabs people's imaginations, even if it's incredibly complicated and, still very much under development.
From what I remember from the video, it basically says that everything, and I mean everything, all the particles, all the forces, everything is made up of these incredibly tiny vibrating strings. And the way they vibrate, that determines what kind of particle or force they are.
You got it. It's the cool analogy. Think of a guitar string, right? Depending on how you pluck it, how you make it vibrate, it creates different notes. Well, in string theory, those different notes, they're the particles and forces we see in the universe.
I like that. So the universe is just a giant cosmic symphony played out by all these tiny strings.
Exactly. But here's the thing about string theory. It introduces some pretty wild ideas, too. Like, for it to work, we actually need more spatial dimensions than the three we're used to experiencing in everyday life, like up, down, left, right, forward, back. We need more than that. But these extra dimensions, they're curled up really, really tiny, so small that we can't even detect them.
Hold on, more dimensions? You're saying there could be like whole universes tucked away in these tiny curled up dimensions. That's even weirder than the multiverse.
Well, it's definitely mind-bending. And the funny thing is, string theory actually connects back to the multiverse idea in a really cool way. See, the different ways those extra dimensions can be curled up, they can lead to different sets of physical laws. So it's like this vast landscape of possibilities with all these different universes, each with its own unique physics. Physicists call it the string landscape.
So string theory is basically saying that there could be like an almost infinite variety of universes, each with its own unique set of rules. That's incredible. But it also raises another big question. Why are we in this particular universe with these specific laws out of all the possibilities? It seems kind of random, doesn't it?
That's a great point. It's what the video called the not problem. And yeah, it's a deep one. Why this universe, out of all the others, some physicists think that maybe eternal inflation is the answer. You know, if new universes are constantly being created in this inflating multiverse, then statistically speaking, it's likely that every possible configuration in that string landscape, it's got to be out there somewhere.
Oh, I see. So the multiverse could be what's actually creating all these potential universes predicted by string theory. It's like the multiverse is the canvas and string theory provides the paint.
Yeah.
And that makes it possible to have all these different cosmic creations, in all these different forms.
That's a beautiful way to think about it. Of course, we have to remember that all of this, string theory and the multiverse, it's still very theoretical. It's really hard to test these ideas directly. And there's a lot of debate among physicists about whether these are even valid scientific ideas.
Fair enough. So where does all this leave us? We've talked about inflation, the multiverse, string theory, this whole landscape of possibility. My head is spinning. But are there any other alternatives? The video did mention some other models that try to explain what came before, ones that maybe don't involve extra dimensions, a zillion copies of ourselves.
You're absolutely right. Not everyone buys into the whole multiverse or string theory thing. And there are some other really cool models out there, each with its own way of tackling the origin of the universe. The video focuses on two of them, the ekpyrotic model and loop quantum gravity.
Okay, yeah, those names ring a bell, but to be honest, I didn't quite grasp them. Can you break it down for me? Like, I'm 5. All right, so we've gone deep into inflation and the whole multiverse concept, even dipped our toes into string theory. All these like mind-blowing ideas about the very, very, very beginning of everything. But the video you sent us, it also goes into some alternative models, right? Some that maybe don't need, like, extra dimensions or gazillion versions of ourselves running around.
You're right. It's not like everyone's on board with the multiverse or string theory. There are definitely other compelling models out there trying to explain the universe's origin in totally different ways. The video highlights two, the ekpyrotic model and loop quantum gravity.
Okay, I remember those names being thrown around, but full disclosure, they kind of went over my head. Can you break them down for us simple folk?
Oh, totally. The ekpyrotic model, that's a really fascinating one. It suggests that our universe, it didn't come from just one big bang. Instead, it's this cyclical process of collisions between these higher dimensional brains.
Brains, like the membranes. I'm picturing soap bubbles. Is that even?
Sort of. Think of our three-dimensional universe as a flat sheet, a brain, floating in a higher dimensional space. Now imagine another brain just hanging out parallel to ours. The ekpyrotic model says that these brains, they can actually collide, and that collision releases this huge amount of energy enough to create, boom, a whole new universe.
So instead of an explosion from a single point, it's more like a crash between these brains. That's a wild visual.
Exactly. And the video actually visualizes it really well. Think of two sheets of paper coming together and bouncing apart. That's basically the idea behind the ekpyrotic model. The energy from that collision, that's what creates the hot, dense conditions we associate with the Big Bang.
So it's like the Big Bang is not the actual beginning, just one stage in this endless loop of brain collisions and expansions, kind of like a cosmic dance, I guess.
It's a beautiful way to put it. Our universe could just be one cycle in this never-ending dance, expanding and contracting over unimaginable amounts of time. And get this model actually explains some of the stuff we see in the universe, like its flatness and how matter's spread out, without even needing inflation.
So it's like the universe has a reset button, going through these cycles of creation and destruction. That's so different from the whole inflation multiverse picture, right? It's like a totally different vibe.
You're right. It definitely offers a different perspective on things. Now, the other model the video talks about, loop quantum gravity, that takes a different approach altogether.
Loop quantum gravity, yeah. The name's familiar, but I'm drawing a blank on what it actually is.
It's a pretty complex theory, but the gist is this. Space and time, they're not actually smooth and continuous like we usually think of them. Instead, they're made up of these teeny tiny discrete units. Like, imagine the pixels on a computer screen.
So instead of a smooth fabric, it's more like a mosaic, made up of these tiny building blocks.
Exactly. And this pixelated nature of space and time, it has some huge implications for how we understand the Big Bang. You see, in those traditional models, the Big Bang starts from a singularity, right? This infinitely small point where all the universe's matter and energy are crammed in.
Right. We talked about that earlier, the point where our physics just goes haywire.
Exactly. But with loop quantum gravity, you can't actually have a true singularity. There's a limit to how much you can squeeze matter and energy together, and that limit's set by the size of those fundamental pixels of spacetime. So in this model, as the universe collapses, it hits a certain point and then, boom, bounces back outward.
It's like a rebound instead of just collapsing into nothing. That's pretty cool.
Yeah, it's like a ball bouncing off a wall. Loop quantum gravity, it basically replaces the Big Bang singularity with a big bounce, suggesting that the universe goes through these cycles of expanding, contracting, and expanding again.
So both these models, the ekpyrotic model and loop quantum gravity, they both point towards this cyclical universe. It's like the universe is breathing, expanding, contracting over these huge cosmic timescales. It's a pretty amazing image.
I love that analogy. It really captures the essence of it.
Yeah.
And even though these models are still very theoretical, they show us that there are multiple ways to approach this whole question of what came before the Big Bang.
Yeah.
The universe might be even weirder and more complex than we can even imagine right now.
It's truly mind-blowing to think about all these possibilities, even if we don't have all the answers yet. But there's this one question I keep coming back to, and it's kind of a big one. Even if we figure out how the Big Bang happened, the mechanism behind it, doesn't the why still remain a mystery? Like, why is there something rather than nothing?
You've hit the nail on the head. That's the ultimate question, isn't it? And the video, it acknowledges that this might actually be beyond the realm of science, at least as we understand it now.
Yeah.
Maybe there just isn't a reason, not in the way that we think of it. Maybe the universe just is, and that's all there is to it.
It's humbling, in a way, to realize that there might be limits to our understanding, that some questions might just stay unanswered no matter how hard we try. But it's also pretty exciting, don't you think? The universe is full of mysteries, and we keep pushing the boundaries of knowledge, trying to unravel them.
Absolutely. It's that curiosity, that drive to explore. That's what keeps science moving forward.
Yeah.
Who knows what incredible discoveries are waiting for us just around the corner.
Well said. This deep dive, it's taken us on a wild ride through some of the most mind-bending concepts in physics. Inflation, the multiverse, colliding brains, the Big Bang. We might not have all the answers, but I think we've gained a new appreciation for just how vast and complex the universe is, and all the possibilities that are out there just waiting to be discovered.
And remember, the journey doesn't end here. The search for answers about the universe's beginning, it's an ongoing adventure. Every new piece of evidence, every new theory, it brings us a little bit closer to understanding our place in this vast, amazing cosmic tapestry.
So to all you listeners out there, keep that curiosity alive. Keep asking those big questions and never lose that sense of awe and wonder at the mysteries of the universe. Who knows what we'll find out there, just beyond the horizon?